All right, recording is rolling. It's Friday, August 12th. All right, and got a short day, so thank you. All right, just got a couple things lined up here. All right, you guys remember yesterday we were looking at these graphs. So I was trying to show you guys some graph tricks, relationships between variables, and probably introduce you guys to a new idea which involved linearization. So I do want to debrief that, go over that. You guys have that page out. And then in a few minutes, I'm going to walk around class and see that you got it right, that you actually got the graph and you got the equation. I'm going to give you guys a stamp for that today. That's how we're doing it. And I'll give you guys credit for that. Great book. And then while I'm doing that, have that going on, I've got going to help you guys set up some flashcards. But let's do one thing at a time here. So first, let's focus on yesterday's stuff. Right, so I had you guys make some measurements about circles yesterday. Right, so you had a bunch of circles printed out. You measured with a ruler what was the radius of the circle. You took some string and some scissors and were able to get the circumference. You counted tiles to estimate what's the area of the circle. And I had to do one more thing, which is to pick up a calculator and square the radius. And that ended up playing into the very last thing that sent you guys out the door with. Right, so then I had you guys make a bunch of graphs. Right, so we got one table and three graphs. That's how it worked. Right? One graph was circumference versus radius, which was a linear relationship. See all these dots? There's a line best fits, just straight line relationship, which should have been no surprise once you see it in retrospect, because it should follow this form: circumference equals 2 pi r. Right? You guys have probably known this since elementary school, but once you see that on a graph and say, okay, if there's a direct relationship, then is say like if you double the radius of a circle, you should double the circumference. If you triple the radius, triple the circumference. That's what a direct relationship is, right? A straight line relationship. Right now, empirically, we got about 6.6 times r. I think this is you guys yesterday, right? It's your paper. And then the textbook answer would have been 2 pi, which is 6.28. It's pretty close to that. Right? Then I had you guys graph the area versus the radius, and that ended up being like a curvy shape. I'll call all graphs curves, even if they're straight lines. It's like a math term to call this, even this you call it curve. Right? But this one actually was curvy, and actually ends up being a parabola because y equals x squared. It's like a parabola. And this is area is proportional to r squared. Okay? Now, how curvy is this parabola? Like, it's not just plain area equals r squared. Like, there's more to it. Something times r squared. Okay? That something could like stretch us up or push us down. It's like, well, that's a really tricky question to answer, unless you know this next trick that we did right at the tail end of class and I sent you guys home with, which is if you manipulate the x-axis, if you actually square the radius and you graph not a versus r, but a versus r squared, then actually these points should line up in a straight line. I did this activity with my other class yesterday too, and let me show you guys that. Oh, okay, this is just another class I picked up. So a versus r squared. See how all the points came out in a straight line? That's why on the table I had you guys have a manipulated column just like the r squared column. You guys see that? Okay. And then many labs and the FRQs on the AP exam, they're going to have you guys do similar things with other physics variables too. Right? These all line up in a straight line. So this line could take the form y equals mx. You guys see that? Y equals mx. Okay. But instead of y, it's a area. I've got the answer right here. This is for another class, so slightly different data. Right? A equals, right? Instead of x, it's r squared, right? Right. And then if you find the slope of the line of best fit, which is just rise over run, that should give you a number popping right here. Is that? You guys see how this is working? So this, I mean, I glanced at this equation of a parabola, right? But then if you have this x-axis manipulated, you can linearize it and very quickly figure out like the slope of a line, right? You guys see that? Pick an equation like that. Now, the ideal answer should have been 3.14 because you guys probably also know since elementary school, area of a circle is pi r squared, right? You guys know this? Right. But of course, in science, there's always going to be a little bit of error in your measurement, so you probably didn't get exactly that. Now, I took your guys' data myself, and I tried and saw, okay, what should you have gotten? At least some of you guys shared some data with me. So anywhere between like 2.3 times r squared up to about 3 times r squared. Now, some of you guys maybe used your own data. So some of you guys showed me stuff you got like exactly 3.14 r squared, which would be like, oh man, that's like dead on. You got counted everything exactly right. Right, but yeah, your graph should have been linearized on a versus r squared, right? And then you should have got something like A equals it's something like this, about 2 or 3, and ideally pi times r squared, right? Okay, you guys can see that? This one? Okay. Right, so here's how we're going to handle this today. Normally I'll pick stuff up from you guys and review it and check stuff off and get stuff in the grade book, but today I'm going to walk around, help you guys out. If you have any questions, I can help you out personally. And if you get it completely right, I'm going to give you a turtle stamp. Oh yeah, turtle stamp. So have your paper out, and if you did everything right, you get a turtle stamp. All right, so while I'm doing that, walking around class, helping you guys out, answering all your questions, make sure you really get this concept going into the weekend. You should see on your desk, you guys have some cardstock cards here, and you also have some of these pages. You guys see these papers? Okay. Now there's one that has like a blank column on the left side, or well, left or right side, depending on which way you're looking. Okay. One that's completely filled. Right? You guys see that? Okay. Do you guys see that these are like ready-made flashcards? Ready-made flashcards. Right. Now, what I would like to. Okay, here's kind of the default Griffin mode. It's like, oh man, I can make this great resource cards. You could just like cut these out and use these as flashcards, right? Okay. Except if you really, really want to learn something, like the more active it is on your part, like the more you are personally writing stuff out, helping each other out, teaching each other, that actually helps you learn this material. Now, one thing is, you got to be familiar with the variables and units that we're using in this class. Now, it'll take us like all semester to get to most of these, and then the ones we don't hit, the semester will hit in January, and then by the end of January, you should know all the variables and units in class, like in context, inflation stuff. Right? But for now, I think a really good takeaway is to at least get the practice of variables and units, because just having taught this class so many years, just some errors that say, oh, dang, but people think like that. Okay, so just to get you guys to set on a straight path, let's say, go ahead. Oh, okay, look, what are some different things you can measure? So do you think you can measure a distance? I mean, you guys were measuring distance yesterday. Suppose you had a length, say a length of like 11 centimeters. You measure something that's 11 centimeters. Do you want to say this? The number of centimeters equals 11. Is that a notation you want to use? No. You want to say the distance. I might use D. I might use X. I put X on these flashcards, right? This distance, displacement, length, might use L length, right, is 11 centimeters. Okay. You guys see how there's a variable and a unit? Okay. All right, so when you see letters like from the alphabet in this class, it might refer to one of two different things. It might be a variable or it might be a unit. Right? And the unit is attached to a number. The variable is like the thing that the quantity that you're trying to measure. Is it? How about another one? Like this mass right here. I got a whole box of lab masses. You guys gonna get your hands on these all throughout the year. Lots of labs. Here's the biggest one. This is 1 kilogram. For context, it's approximately 2.2 pounds, but we're not going to use pounds. We're going to use metric system. Talk about that next week. But 1 kilogram. Right. So suppose you had like 3 of these. What do you want to say? The number of kilograms equals 3. Is that what you want to do? You want to say mass equals 3 kilograms. Bing! Look at that. Variable, unit, kilograms to the unit. Right? You guys see how it's working? Right, so the variable equals some number of a unit. Right? That's it. How about if 9 seconds have passed? Do you want to say the number of seconds equals 9? How about time equals 9 seconds? Bing! Right? Guess how it's working? Right, variable unit. Right, so you guys get to have practice doing it, actually like writing it down with your hand, which is going to build neural connections in your brain and help you guys out in this class. So there's 2 separate pages of these. I gave you guys cardstock. Take the rest of the class today, help each other out, make these flashcards. There's also scissors on your desk so that after you make these, if you copy down these exactly, like here, I want to show you guys if this does work. You guys see F? What do you guys think F stands for in this class? Force. Force, good call. You guys are on. Right? A force is just a push or a pull. That's all it is. If I push on these scissors, that's a force. And what are you going to measure force in? Well, let's see, if I flip this over, newtons, right? Now, Newton is the composite unit. It actually breaks down into kilogram times meters per second squared. That'll make sense in a few weeks. But all right, so that's what we got now. So, I gave you guys an example here. Now, if you don't want to write EG, you don't have to. It's like some Latin phrase, just means for example. Right? Force equals 3 newtons. Hey, that looks exactly like the bunch of examples I just gave you, right? Variable equals some number times a unit, or sorry, of a unit, I should say, right? Okay, like force equals 3.0 newtons. Ah, yeah, you guys got it. One of many things I have to go over with you guys next week, but since it's up here, may as well mention it. Is there a difference between 3 newtons and 3.0 newtons?
Kind of.
Yeah, what's the difference? What does the 0.0 mean? It means
Very accurate.
yeah, it means you have more precision. It means you actually have that knowledge. See, if I just write 3 newtons, it's like, well, it might be 3, it might be 3.1, it might be 2.8. Those all kind of round to 3. But if I say 3.0, that means I do have to the 10th place that level of precision. I know it's not 3.1. I know it is 3.0. Okay. Okay. And this might actually be 3.04 for all I know, because I don't have the next unit precision. All right. So I give you guys rest of class. Again, we got a short day going on. So go ahead and make your cards. We're gonna walk around, help you guys out.